All right, hello everyone. Today we are going to be talking about Thevenin and Norton equivalent circuits as well as source transformation. All right, let's get straight to it. So with Thevenin and Norton equivalent circuits, the big concept is you have a circuit, let's say CIRC for circuit, and let's say you measure the voltage at two random nodes, call it A, B, plus, minus, okay? The whole concept of Thevenin and Norton equivalent circuit is that you can then simplify the circuit to have some said voltage source in series to a resistor, where the voltage source is called the Thevenin voltage, which is also equal to the open circuit voltage VAB, so they're equal to each other. Some Thevenin resistance, and you can also go from this circuit drawing on the left-hand side to a Norton equivalent circuit. A plus, B minus, VAB, which is equal to V Thevenin. This is Rn. This is the Norton current. Now, how are they all related? Well, if you took a short circuit current, so you connect node A to node B with this short circuit current called ISC. That is what allows you to then derive, not shown here in this YouTube video, the Thevenin equivalent circuit and the Norton equivalent circuit. So the Thevenin equivalent circuit is a equivalence or a simplification of this drawing where you have been able to derive the Thevenin voltage across node A, node B when it was open, and you have derived some Thevenin resistance that represents the resistance of that circuit, again shown here. Now, sometimes you want to be thinking about current, so if you were to draw the short circuit current, ISC, then that allows you to go to the second drawing where IN is equal to ISC, and you can find the equivalent resistance, Rn, which would be parallel to that current value that you found. Now, how are these two related to each other? Well, V Thevenin is equal to IN times Rn. You can also say is equal to ISC times R Thevenin, because IN is equal to ISC and Rn is equal to R Thevenin. This is how Thevenin equivalent and Norton equivalent circuits are related to each other. Again, the derivation, the conceptual understanding of the physics, the electromagnetics, the proof of this is not done in this video. I'm just showing that the top drawing here is a Thevenin equivalent circuit, the bottom one Norton equivalent circuit, and the relation is provided by this equation that I have put the curly bracket on. So V Thevenin is equal to IN times Rn, also known as ISC times R Thevenin. Now, usually with Thevenin and Norton equivalent circuits, you are asked to solve for, four items. One of them is V Thevenin. How do you do that? To solve for V Thevenin, use any or all laws and analysis of circuits. What do I mean by that? I mean Ohm's law, voltage divider law, current divider law, Kirchhoff's voltage law, Kirchhoff's current law. You can use mesh and node analysis to solve for V Thevenin, which is the open circuit voltage across node AB. Okay. You can also use some simplification, like if you have, so you could use simplification. where if you have, let's say, rest of circuit is drawn, you have some R parallel and then some R series, and then you have the node AB that's open. So if you were solving for Thevenin, you can simplify and replace the drawing now with rest of circuit. You could replace it with this drawing. Why? Because if you look at RS is in series with an open circuit voltage. No current flows through RS. Therefore, the voltage drop across the RS is 0. So you can replace it with a wire. So you have simplified the left to the right circuit drawing by replacing RS as a wire. Now, Thevenin is equal to the voltage across Rp, the resistor that's in parallel to the open circuit voltage. Sometimes you want to solve for Isc, which is equal to In. And you can do that by using any or all laws and analysis of circuits, like I said earlier, Ohm's law, Kirchhoff voltage law, Kirchhoff's current law, voltage divider law, current divider law, mesh node analysis. You can also use simplification. For example, you may sometimes have rest of circuit Rp, A plus, B minus. You can replace this drawing with the following: rest of circuit. My apologies. Rest of circuit. Now, in the left-hand drawing, you have Rp, in parallel to the short circuit current. If you remember from your Physics 2 class, current likes to flow through the path with minimal resistance. Therefore, current will not, this current, call it Ix, will not flow through Rp. Because nothing is going to flow through Rp, you can remove it from the circuit, which leaves you with drawing on the right-hand side. And you continue to use any laws or analysis to solve for Isc. You will also be asked to solve for Thevenin. The way you do that is zero out all your sources and then solve for the R equivalent, which is equal to Thevenin, between nodes A and B. Quick comment. Voltage sources become, by zero out process. So by zeroing out, Vs becomes a wire, also known as a short circuit. But we're just going to call it wire from now on. Current sources become, by the zeroing out process, an open circuit. Let's say the node X was at top, node Y was at the bottom. So now you have the plus and minus terminals as drawn. And this is an open circuit. Again, it's just called VXY because we're assuming X has a higher voltage than Y, and the positive terminals at the top, minus at the bottom. Okay? So a voltage source has a non-zero voltage drop. To make it zeroed out, you have to make it become a zero voltage drop. A zero voltage drop is a wire. Wires have zero voltages dropped across it. A current source has non-zero current flowing through a part of a circuit. to make it become 0, you have to replace it or substitute it with an open circuit, because open circuits do not have current flowing through it. You don't see electricity flowing through air. You should not. So that is how you do our Thevenin. Zero out all your sources first, and then solve for R equivalent between nodes A and B. The last thing that you will be asked to solve for is what Rload in a Thevenin or Norton equivalent circuit will achieve max power at load. We are not going to derive this, but I will say, therefore, if you have simplified any circuit to the Thevenin equivalent drawing, or the Norton, here, drawn on the right-hand side. Okay, and let's say you put a RL, which is R load. The maximum power at that load is achieved when R load is equal to R Thevenin. I'm not going to derive it here, but that is the case. Okay, so let's recap. Thevenin and Norton equivalent circuits are two equivalent circuits, top and bottom drawn here, that allow us to redraw a circuit in which you randomly decided to measure a voltage between node A and B, and you set that equal to the Thevenin voltage. And using Thevenin equivalent and Norton equivalent circuit analysis, you can redraw it or simplify it to any of these two drawings to your liking. The relationship between these two circuits that are equal to each other is shown here. V Thevenin is equal to the Norton current times a resistance called R Thevenin or R Norton. It's also important to know that Rn is equal to R Thevenin, In is equal to Isc. Another way to do this is if you wanted to, like I said earlier, I had it drawn but I erased it. If you just shorted the node, that's where Isc comes from, okay? Now, in exams or homeworks, wherever you go in undergrad or grad school, you will have to find V Thevenin, where you can use any or all the laws and analyses taught in circuits like Ohm's law, Voltage's law, current divider law, Kirchhoff's voltage law, Kirchhoff's current law, mesh and node. You can use those to solve for V Thevenin. You can also use a simplification where if you have an R in series to your open circuit voltage, you can replace that with the wire. You can solve for the short circuit current or the Norton current. Again, use any laws or analyses. You can also use simplification where you replace a resistor that's in parallel to the short circuit current by just removing it. You will also be asked to solve for R Thevenin. How do you do that? Zero out all your sources and then solve for the R equivalent or R Thevenin value between nodes A and B. To be very clear, you zero out a voltage source by replacing it as a wire. You replace a current source with an open circuit voltage. The last thing that you'll be asked to solve for sometimes is what load resistance will maximize power at the load if you insert it in a Norton equivalent or Thevenin equivalent circuit. And I'm telling you, it's R load equal to R Thevenin. Okay, last thing I want to talk about before we do practice problems is source transformation. Source transformation is actually source substitution. Substitution. It's when you are allowed to replace a Thevenin equivalent circuit with a Norton equivalent circuit and vice versa in any sub-region in a circuit between two nodes. Let me show you an example. Let's say I have this circuit. Okay. Let's call this Vs. Let's call this R1. This node, or this region of the circuit, looks like a Thevenin equivalent circuit. Look here. You see the Thevenin, you see R Thevenin, or more specifically, let's look at this drawing right here. Thevenin, R Thevenin, they're in series and they're connected to two nodes. Same thing. We can put our imaginary alpha and our imaginary beta right here. Source transformation, or what I like to call source substitution, allows me source transformation allows me to transform the circuit such that now I have you see how what I circled on the left hand side has been replaced by what's on the right hand side. This is R1 and this is Is, where Is is equal to Vs divided by R1. Why? Because this is like saying it's very synonymous to Isc is equal to V Thevenin divided by R Thevenin. Where on the left hand side, one can argue that Vs was equal to V Thevenin, R1 was equal to R Thevenin. Using source transformation, I was able to replace this voltage source that was in series with R1 I was able to replace it with a current source in parallel with a resistor as what a Norton equivalent circuit is, right? So Is is equal to Vs divided by R1 because it's synonymous to Isc, which is equal to V Thevenin divided by R Thevenin. That is what source transformation is. It is when you are allowed to substitute a sub-region of a circuit where you witness a Thevenin equivalent circuit, you can transform that to a Norton equivalent circuit, or vice versa. You use this concept to your advantage to solve for any kind of value in a circuit. For example, at universities, they'll give you a complex circuit and they're like, what's the voltage across this random resistor? And it would help you if you use source transformation to complete any analysis or laws to solve for the voltage across a random resistor. I will show you as we do practice problems. But up until now, I have explained Thevenin equivalent circuit, Norton equivalent circuit, and source transformation. So let's do an example. Example I would like to do is, I'm going to call example number 1. I have this beautiful circuit. This is going to be solved algebraically. Okay, first question number 1. What is R Thevenin? Okay, steps. R Thevenin is what we are solving for, and let's solve it for in units of ohms. Cool. Second step, how do I solve for R Thevenin? You need to zero out sources, where voltage sources, that's the only type that we have in this drawing, becomes a wire. So let's do that. We did it. If you look here, this is just a wire. No longer do we have a voltage source. Now we need to find R Thevenin, which is R equivalent between nodes A and B. So let's do that. Simplify this drawing. Well, we notice R1 started from the bottom. Now my whole team here, R1 and R2 are in the same team because it started from the same bottom and at the same top nodes. And that means we have R1 in parallel to R2 as a new resistor, and they're connected to R3 as so. Now we notice that R1, which is in parallel to R2, that as a system is in series with R3, so we can simplify the drawing further, call this R Thevenin, where R Thevenin is equal to R1 and parallel to R2, all of that is in series with R3. Mathematically speaking, that would look like R1 times R2 divided by R1 plus R2 plus R3. That's R Thevenin. Next question. Question number 2. What is ISC? Let me redraw the drawing. The circuit, I mean. Now, we're being asked to solve for ISC in units of amps, let's say. You can use any law or analysis to do this. Okay? We're trying to solve for ISC. I don't know the current flowing through here. Let's call it Ix. And then I do not know the current flowing through R2. Let's call it I2. But I'm going to use current divider's law. I'm going to show you why. Using current divider law, ISC must be equal to Ix divided by R2 plus R3 times R2. Remember, this is ISC, this is I2, this is Ix. Ix is the one that's going to split up. How do we solve for Ix? Because that's the one missing. We have one equation, two unknowns. Two unknowns. We need to find Ix. So that's my third step. Well, can you simplify the circuit to find Ix? Yes. You notice that R2 is in parallel to R3 because you've implemented this short circuit current. So, you can even simplify it further so that you now have just one resistor. But this is R1 plus R2 parallel to R3. This is Vs. You can use Ohm's law to solve for Ix. So Ix is going to be equal to Vs divided by R1 plus R2 parallel to R3. Which means, if you go back here, ISC is equal to Vs divided by R1 plus R2 parallel to R3. That whole thing divided by R2 plus R3 times R2. That's ISC. And we know R1, if we were given R1, R2, R3, and Vs, which was in the drawing, we could solve for ISC. And the usual next question is question 3. What is Thevenin? Okay, Thevenin. So maybe we were going for units and volts. Well, we know Thevenin is equal to ISC times R Thevenin. So that means it's equal to Vs divided by R1 plus R2 parallel to R3 divided by R2 plus R3 times R2 times R Thevenin, which is what? R1 times R2 divided by R1 plus R2, all of that plus R3. This whole thing is equal to Thevenin. Because this is ISC and this is R Thevenin. See? And I think that's enough for me to explain that if you, again, we were given this circuit in the beginning. We were asked for R Thevenin. Zeroed out the sources, found the equivalent resistance between those A and B, called it R Thevenin. We did that. ISC, we had to draw that short circuit current down from node A to node B. It's always down, by the way. It's always down. From A to B. It's always from node A to B. And I said, let's use current divider law, but we had a current missing Ix, so we simplified the circuit drawing by noticing that R2 and R3 are in parallel to each other. That's what we did here. And then we took it one step further by noticing that R1 and this system of resistors were in series with each other. Then we used Ohm's law. Then we plugged and chugged, where the 1 in square bracket is, no, sorry. What's in parentheses is Ix divided by R2 plus R3 times R2. Then we said, what if we wanted to know Thevenin? So Thevenin is equal to, using the Thevenin and Norton equivalent circuits concepts, Thevenin is equal to Isc times Thevenin. And so we just substituted again what we got for Isc and what we got for Thevenin. That's how we got Thevenin. Now let's do a special example. I'm going to call this example problem number 211-1. Okay, let's say I'm given this drawing. Say this is Vs, 1, 2, 3, 4. Vs is equal to 15 volts. And R1 is equal to R2, which is equal to R3, which is equal to R4, which is equal to 15 ohms. All right, let's say that's the case. And the first question being asked is, what is Thevenin? Okay, there's a protocol to follow, which I've been teaching. Okay, so what is Thevenin in units of ohms? First, you need to zero out your sources. All right, so let's redraw the circuit. We have a voltage source here. It becomes a wire. It becomes a wire. Here's R1, here's R2, here's R3, here's R4, R1, R2, R3, R4. Here's node A, here's node B. Now simplify this circuit. I like to work from out to in. In being which nodes am I solving between node A and node B? It happens to be on my right-hand side, so I like to work from the left-hand side. I notice that R1 and R2 are in parallel. R1 is in parallel to R2. And I redraw the rest of the circuit. Then I notice that R3 is in series to R1 parallel to R2. So this is now R1 parallel to R2 plus R3. This is R4. This is A. This is B. And then I just have the Thevenin, which is equal to what? This whole thing in parallel to R4. So it'd be R1 parallel to R2. That whole thing plus R3. This whole thing parallel to R4. R1 is in parallel to R2. That is in series to R3. That whole thing is in parallel to R4, which mathematically would be equal to R1 times R2 divided by R1 plus R2, all of that plus R3 times R4. R1 times R2, R1 divided by R1 plus R2 plus R3 plus R4. There you go. This whole thing is equal to Thevenin, which actually comes out to 9 ohms. If you use all resistors is equal to 15 volts. Okay, cool. Again, what did we do? We looked at the circuit. We were solving for Thevenin, so we zeroed out my source. The voltage source became a wire, as shown here. Then we solve for R equivalent between node A and B. I notice R1 and R2 are in parallel. I notice R1 and R2, which are in parallel, was in series to R3. And then lastly, I noticed that R1 is parallel to R2, which is in series to R3, and that whole thing is in parallel to R4. Cool. Next question. Wait. Whoa. Question. What is question number 2? So this was question number 1. Yeah. Question number 2. What is ISC in units of amps? So let's redraw the circuit. Here's R4, here's R3, here's R2, here's R1, here's VS. Okay? So now what do we do? Well, we can, let me look at my notes. We can, well, first, what are we solving for? We're solving for ISC in units of amps. What can we do? Well, we notice in this region that the short circuit current is in parallel to R4. So we can remove R4 because no current is going to flow through it because current chooses the path with least resistance. So we redraw, remove R4. And that drawing now looks like A plus B minus R3, R2, and VS, ISE. And we actually did this in the previous problem, but I'll go through it again. Now we have to use laws or analyses. You can use mesh analysis if you want to. I don't like mesh analysis. You can, I don't see how one can use node analysis. But my first impression is to do current divided law because I think of a current leaving the battery called IX. It flows to R1. It's about a split between what I call I2 and ISC. Because I2 and IX, they weren't drawn. The current directions weren't drawn. I have the freedom to draw them. And now I could just use current divided law, which is ISC is equal to IX divided by R2 plus R3 times R2. Because R2 and R3 are parallel to each other. Start from the bottom, now my whole team here. They're parallel to each other. So we have now one equation and two unknowns. So using the third step, I'm going to simplify the circuit even further. Simplify circuit to find IX. I noticed that I actually already said that R2 and R3 are parallel to each other. So plus minus R1, R2 parallel to R3, but I could take that even further and just have one equivalent resistor where it's R1 plus R2 parallel to R3. Excuse me. And using Ohm's law, I could find IX. IX is equal to Vs divided by R1 plus, parenthesis, R2 parallel to R3. Okay? And if you go back to this equation here, just apply the equation derived from Ohm's law to the equation applied from CDL, current divided law. So fourth step, put it all together. ISC is equal to Vs divided by R1 plus R2 parallel to R3. No, let's not. Hold on. Let's not do that. Okay. So this whole thing, all of that divided by R2 plus R3, and all of that multiplied by R3. And the things that are in parentheses, that's IX. Okay? and that is ISC. So ISC, using the numbers provided to us, which was a little up here, using these numbers, Vs is equal to 15, all the R is equal to 15 ohms, you will get that ISC is equal to 0.33333333 amps. Now, next question. What is Thevenin? Okay, we're solving for Thevenin in units of volts. What can we use? We can use Thevenin is equal to ISC times R Thevenin. Okay? And that would be 0.333333 amps times 9 ohms, which gives you about 9 volts. That's it, right? Yeah, that is it. Next special problem. Example number 2, 12, 6. R, I, okay, this is terrible. Sorry. Okay, and we have R minus plus, this is a resistor. This is a resistor. A plus, B minus, R3, I1, R1. Let me look at my notes. Okay. And we are told that I1 is equal to 80 milliamps, V1 is equal to 12 volts, R1 is equal to 50 ohms, R2 is equal to 30 ohms, and R3 is equal to 80 ohms. So I1 is 80 milliamps, V1 is 12 volts, R1 is 50 ohms, R2 is 30 ohms, R3 is 80 ohms. First question for this problem is, question number 1, what is Rth Thevenin? Okay, we're solving for Rth Thevenin in units of ohms, and we need to zero out our sources. Our current source becomes an open circuit, our voltage source becomes a wire. Redraw that. So we have to redraw the circuit now that we've zeroed out our sources. Here's R3, here's R2, here's R1. Notice how the current source has disappeared and the voltage source has disappeared because it has become a wire. So, current source became open circuit, voltage source became a wire. Now, solve for the R equivalent, how did I say it last time? R Thevenin is equal to the R equivalent between node A and B. Okay, let's do that. R1 and R2, they're in series. They look like a human centipede. Now, this R1 and R2 that are in series, that is in parallel to R3. Therefore, R Thevenin is equal to R1 plus R2, this whole thing, parallel to R3. So mathematically, R Thevenin is equal to R1 plus R2 in parentheses times R3 divided by R1 plus R2 plus R3. And that will give you 40 ohms. Ta-da! Cool. Next. So, in this circuit, R Thevenin is equal to 40 ohms. We zeroed out our sources. We found the equivalent resistance between nodes A and B. Next question. Question number 2. What is ISC? Now, let me redraw the circuit. Nope. So we are solving for the short circuit ISC. Okay, how do we do this? Well, how many sources do you see in the circuit? 2 sources. One voltage source, one current source. This is an opinion, okay? But I don't like working with current sources, and I don't like mesh analysis. I do not. So that being said, I will be thinking and brainstorming to avoid working with current sources and avoid working with mesh analysis. First, can I simplify this circuit? Yes. This resistor R3 is in parallel to the short circuit current, meaning I can remove R3. So I'm going to simplify. So I am removing R3. Now, looking at this circuit, I don't like working with current sources. My whole goal is to find ISC. If I wanted to, you could use mesh analysis, perhaps. I don't know. You could use mesh analysis. I don't like working with mesh analysis. I don't see how one would use node analysis, because node analysis is often used to find voltages. But you could use mesh analysis. I don't want to. Instead, I am going to look between this node and this node. Do you see the current source that is in parallel to a resistor, which is also known as aka a Norton equivalent circuit? Which means I can exploit source transformation by substituting a Thevenin equivalent circuit in that red circled region. That is not a voltage source. Where now I have I1 times R1, R1, R2, V1, ISC. Again, I was looking at this region between here and here. I didn't mess anything up on the non-circled red region. Within the circle red region, I have substituted or source transformed this Norton equivalent circuit with this Thevenin equivalent circuit. That is what I have done. And in doing so, in my own personal opinion, I believe I've simplified this circuit problem, because now I have one loop, and I have 1, 2, 3, 4, 5 knowns and one unknown. I don't know ISC, and I have one loop. What can I use? KVL. KVL allows me to state plus I1 R1. I'm going clockwise. Minus R1 times what current? ISC. Because if you use your pencil finger, ISC is flowing through all of these elements. So ISC is the current flowing in clockwise. So I have plus I1 times R1, minus R1 times ISC, minus R2 times ISC, plus V1, because I'm going in the bottom of the mountain to the top of the mountain. Top is the positive terminal, which is on the right-hand side. And all of this is equal to 0 volts. And then, using some high school level algebra, let's dig into this. This is I1 R1 plus V1 equal to R1 ISC plus R2 ISC. So I took the terms related to ISC and put on the right-hand side. Now I'm going to factor out ISC on the right-hand side. I still have I1 R1 plus V1 left-hand side. I'm going to divide both sides by R1 plus R2. So I have I1 R1 plus V1 divided by R1 plus R2. All of that is equal to ISC. And fun fact, ISC is equal to wait one second. I have it in my notes. Isc is equal to one second, y'all. I wrote it down. Oh no. I didn't solve for it algebraically. One second. It would be 0.2 amps. Ta-da. There you go. What did we do in this problem? We were asked to solve for Isc in this circuit right here. So we drew the Isc going down from node A to node B, because it's always going from A to B. And then we simplified the circuit to this drawing by removing R3, because R3 was in parallel to the short circuit current. And then using this circuit, we realized in the red circle region that we have a Norton equivalent circuit as a sub-region of this whole circuit. And so focusing on that sub-region, I was able to substitute the Norton equivalent circuit with a Thevenin equivalent circuit, this voltage source in series to R1. What is that voltage? It's I1 times R1, because V Thevenin is equal to Isc times R1. In this sub-region, it was V sub-region Thevenin is equal to I1 times R1. Sub-region Thevenin was equal to I1 times R1. That's what we got here. And then we notice that we have one loop, 5 knowns, because we know I1, R1, R2, V1. So that's 1, 2, 3, 4, 4 known. One loop, 4 knowns, 1 unknown. We don't know Isc. So we did KVL, and we did it clockwise. So it was plus I1, R1, minus R1 times Isc, minus R2 Isc, plus V1, because of the direction we're going clockwise, up the mountain. All of that equal to 0 volts. We conducted high school level algebra. I explained this already. And we got Isc is equal to 0.2 amps. Good job. Next question. Question number 3. What Rload value achieves maximum power at load in circuit? You don't even need to look at the circuit. I understand it was this circuit. For my visual people, I know it looked like this. But we were able to simplify this to, I'm a Thevenin equivalent opinion-based person, so you were able to convert it to this one, where V Thevenin is equal to Isc, which we found, times R Thevenin, which we also found. So if we put an RL, Rload, in here, using what I taught in the beginning of this video, Rload would have to be equal to R Thevenin to achieve max Pload, which is equal to 40 ohms. And there you have it. All right. One thing. This is example number 1. So going back to example number 1. Okay, going back to example number 1. We had this voltage source, we had this resistor, this resistor, plus, that is messing me up. We had this beautiful drawing, okay, Vs, R1, R2, R3. We didn't have numbers, we were doing this algebraically. I just want to point something out. If the question was, let's say my second question was what is V Thevenin, all right? Let's say, actually, you don't even need to know R Thevenin. But assume we were asked first, what is V Thevenin? Because if you go back, we were first asked, what is R Thevenin? See? No, wait. Okay. We had this example number 1. We were asked, what is V Thevenin? Then we were asked, what is Isc? So I am saying, imagine we were asked, what is our Thevenin? But then the second question was, what is Vth Thevenin? How would you go about it? So don't forget, VAB is equal to Vth Thevenin. To do this, we're solving for Vth Thevenin in units of volts. So simplify the circuit first. Why, Mr. C? Because R3 is in series with an open circuit voltage. Replace R3 with a wire. If you do that, you will get a voltage source, a resistor, R1, R2, and now you have A and B node. How do you find Vth Thevenin? You use voltage divider law, because Vth Thevenin is equal to VR2, which is equal to Vs divided by R1 plus R2 times R2. So I just want to point out, in that problem, if you were asked to solve for Vth Thevenin first, you could get it this way. Okay? And then you could solve for Isc if question 3 was, what is Isc? Vth Thevenin is equal to Isc times R Thevenin. You already solved for R Thevenin. So Isc is equal to Vth Thevenin over R Thevenin, which is, this is Vth Thevenin, and we already found R Thevenin, so you would have been able to do it. The reason why I mentioned this is because when you are given any circuit problem, like let's say, let's just go back to example number 1. Where are you? Right here. In an exam, in a homework, in life, you might see this circuit. And chances are they want R Thevenin, Vth Thevenin, and Isc. You don't have to answer in order. If you want, you could solve for R Thevenin first. That's usually what I do. And then you can decide if you want to go and find Vth Thevenin or if you want to find Isc. Sometimes it's preferred to find Vth Thevenin. Sometimes it's preferred to find Isc. It's whatever floats your boat. But once you have R Thevenin and either or, you can find the missing one. And we already know that Rload is always equal to R Thevenin to maximize Pload. All right, thank you for tuning in. Have a nice day or evening.